So let's see what happens when we stitch together these ideas of heats of sublimation, heats of vaporization, heats of fusion, and also the idea of heat capacity. If we want to know how much energy is required to change from a particular temperature to another temperature, we need to consider every process along the way. Now in this example, let's say that we're going to start out with water that's currently steam. We've got it heat up to 130 degrees Celsius. My final goal here is to say, let's find out how much energy is needed to get to negative 40 degrees Celsius. Well, we're going to have to remove a heck of a lot of heat from that system. And that's probably no surprise to us because we're saying we're starting out with hot steam. In other words, not just at the boiling point steam. We've got steam that's heated up beyond that. And we actually want to cool it down to not only be ice, but we want it to be colder ice. Now remember, if that's still a weird idea to you, that ice can be colder than 0 degrees Celsius, I want to remind you that you've held chunks of steel in your hand before. And steel melts at a very high temperature. You can have solid steel from the moment that it froze at the boiling point, or melting point of iron, really hot, all the way down to room temperature and well below that. Once you've got it in a state of matter, until you hit a phase change, it's going to be that state of matter. Steel is frozen under the conditions we ever touch it, and water is frozen once it's 0 Celsius and anything below. It can be colder than 0 degrees Celsius. Always remember that. You can have cold ice, and you can have quote-unquote warm ice. It's just that once it gets above 0 Celsius, it's not going to be ice anymore. Now, let's think through the processes involved in cooling it. If we want to go from 130 degrees Celsius to 100 degrees Celsius, I hope you remember from what we did in thermochemistry that we're talking about a material here. We're talking about H2O, gas phase. And so, if I want to know what amount of heat energy needs to be removed to cause a certain delta T for a single material, what do we want to do? We want to go grab a heat capacity. Now, depending on what information we have, we may grab a molar heat capacity, we may grab a specific heat capacity, or maybe we were just told what the heat capacity was. Any of those three things would do. And we would just use it as a conversion factor to say, for this much change in temperature, from 130 to 100 degrees, I will have this much heat energy come out. And that's just using heat capacity to determine it. And so we'll just plug those numbers in and we'll get the answer to that part. But we can't just keep going. What we have to do now, if we're trying to figure out the energy to get to negative 40, now we have to figure out how much heat energy we have to remove to go from immediately at 100 degrees Celsius steam to immediately at 100 degrees water. Remember that you can have it right there in infinitely small spacing away from that temperature. Really what we're saying is that we're taking away just enough heat energy to get this molecule to stick, and then this one to stick, and hopefully already this one to stick, and then that one, etc., etc. In other words, we're staying at the same temperature, though, for the gas. We're just getting other ones to start sticking down here. And it's going to have just a tiny bit less heat energy here, but it's still going to be called the same temperature. So as we're getting these to stick, we're just removing some extra kinetic energy. That is our enthalpy of vaporization. In this case, we're going to be using it going to a colder temperature. So we still call it enthalpy of vaporization. We just have to make sure we get our sign right. And here, we have to actually remove heat energy from the system to get it to go from gas to liquid. So we'll grab our enthalpy of vaporization. We'll multiply that times the number of moles that we have there, and that will tell me how much heat energy was needed to be removed to make that happen. So we found out the amount of heat to remove for this temperature change. We found out the heat to remove just to get it from gas to liquid. Now we do heat capacity again to get from almost boiling temperature, well, at boiling temperature water, down to at freezing temperature water. So now we're just using heat capacity of water and delta T to find out how much heat energy we had to remove again. Now I'll point out that here and here on our axes, we did a little broken axis because this range would have been much longer than would have fit on the scale of our page. So we just did that so we didn't have to use up as much room on our diagram, but of course our calculator doesn't have that issue, so it wouldn't matter in our calculation. So we're right here at 0.00001 degrees Celsius water. We're going to have it start freezing now. How much heat energy is required to go from 0 degrees Celsius liquid to 0 degrees Celsius solid water? And that's going to be your enthalpy of fusion. So again, we just calculate that one. The last step will once again be heat capacity. So we'll use heat capacity of ice, water solid phase, and we'll find out how much energy is needed to go delta T of negative 40 degrees. That's the way that you would actually handle one of these problems. For each of these sections, this is a pretty straightforward problem that we've been doing a lot from our thermochemistry section, and in this case also just by adding in the number for enthalpy of vaporization times the number of moles. We'll see an example of that in our homework set, and we want to make sure that we understand this process as well.